The topic surds. What is a surd? A surd is an irrational number that can be expressed in its root form. And what is the difference between a rational number and an irrational number? Rational numbers are those that can be expressed as simple fractions in the form a over b, where a and b are integers and b is not equal to 0. Let's just say that all integers are rational numbers since they can be expressed with the denominator of 1. For instance, negative 2 over 1, negative 3 over 1, 2 over 1, 3 over 1. All these are rational numbers. And for the sake of this topic, roots of square numbers will also be rational. For instance, a number like, let's say, root 4. Root 4 is a rational number since we know its solution to be equal to 2. Root 9 will also be rational because we know the solution will be equal to 3. What about irrational numbers? These ones cannot be expressed as simple fractions, and for the sake of this topic, when roots of numbers are expressed as decimals, they neither terminate nor recur, and these are what we call surds. For instance, root 2, root 3, root 5, root 6, and so on. Let's consider the terms that are used in surds. The first one, conjugate. We say that two surds are conjugate of each other if their product is a rational number. For instance, in part A, what is the conjugate of root 3? The conjugate of root 3 has to be root 3 itself. Why? When you multiply root 3 by itself, it simply means you are squaring that surd, and therefore the square root sign will be eliminated by the square here. You end up with 3, which is a rational number. And then in part B, I've considered an expression here in form of a binomial. So what is the conjugate of this expression? The conjugate of this expression will have to be root 2 plus root 3. Let's remind ourselves of the concept of difference of two squares. You remember the 3 quadratic identities? These are the only 3 ways that you can expand a binomial, where you have a plus b to be multiplied by itself, or you can have a binomial a minus b to multiply itself, or you can have a binomial where there is a positive sign to multiply another binomial with the same terms but now with a negative sign. So in this instance here, when we do the expansion, we are going to arrive at a squared minus b squared, and this is what we refer to as the difference of two squares. And how can we apply the concept of difference of two squares here? Let root 2 be represented by a, and let root 3 be represented by the letter b. So we'll be in a position to capture here that this is similar to having a minus b to multiply a plus b as expressions. And since the solution here is a squared minus b squared, we'll be in a position to say that the expansion here will simply be root 2 squared to subtract root 3 squared. And the solution here will be 2 minus 3, which is equal to negative 1. And negative 1 here is a rational number. The second word here, rationalization. This is the process of multiplying a surd, which is an irrational number, by its conjugate to get a rational number. And what does it mean to rationalize the denominator? This is when you are dealing with the fractional surd, where you end up expressing it in such a way that the denominator does not have a surd. In simple terms, it's like we are getting rid of the root sign on the denominator. For instance, we can consider a fraction like 1 divided by root 3. We know that the conjugate of root 3 will be root 3 itself. And therefore, what we multiply on the denominator, we also multiply on the numerator, so that we end up with that. And therefore, on the denominator side, we know that when you multiply root 3 by itself, we end up having the denominator 3, which is a rational number. And therefore, on the numerator side, you are going to have 1 to multiply root 3, which will simply be root 3. And this is what we refer to as rationalizing the denominator. Let's consider simplification of surds. From what we've learnt about surds, we can easily conclude that all prime numbers will be surds, and therefore, this is how we can simplify surds. Let's see how we can simplify surds using prime factorization. For instance, the first one here, let's consider the prime factorization of 63. So we can be in a position to say 63 divided by 3, it will be 21, and then 21 can be divided by 3 to get 7, and 7 can be divided by 7 to get 1. And therefore, root 63 can be written as root 3 multiplied by root 3 multiplied by root 7. And since we know that when you have a root and then you multiply by itself, you end up getting a rational number. So here root 3 multiplied by root 3 will simply be 3, and then we consider root 7. And this is the simplification of this surd. Another number, root 48. Let's consider the prime factorization of 48. So this being an even number, we can start by dividing by 2 to get 24. And then we divide by 2 to get 12. And then we can divide it by 2 to get 6. And then by 2 again to get 3. And then by 3 to get 1. So this one can be written as root 2 multiplied by root 2 multiplied by root 2 multiplied by root 2, root 2, and then multiplied by root 3. So when it comes to solution, these two surds here will give us the number 2, multiplied by these other 2 also will give us a rational number 2, and then we'll have multiplied by root 3. So the simplification will end up giving us our answer as 4 root 3. Another surd is 104, and therefore when you consider the prime factorization, you end up with root 2 multiplied by root 2 multiplied by root 2, and then multiplied by root 13. And then I've considered the fact that root 2 multiplied by root 2 is 2, which is a rational number here. But then, since there's nothing you can do to the other remaining roots, you combine them again to end up with root 26. So the solution here is 2 root 26. And then the last number that I've considered is root 252. So this is its prime factorization. So we end up with root 2 multiplied by root 2 multiplied by root 3 multiplied by root 3, and then multiplied by root 7. So from what you can see here is when you multiply root 2 by itself, you end up with 2. When you multiply root 3 by itself, you end up with 3. And then there's nothing you can do to root 7, so it remains there. So when you combine these numbers, you end up with 6 root 7. And this is the solution. Operations involving surds. Let's begin with addition and subtraction of surds. Let's look at these four expressions and let them guide us to understand exactly what we do with surds when it comes to addition and subtraction. So from the first expression, you can see that we are having the unknown x in each term. So we'll be in a position to say that we are dealing with like terms here. And like terms, when you're having like terms, we add the coefficients. So we end up with the answer here, 5x. So now, let x be a surd so that we see how we perform operations involving surds when it comes to addition. So, when you have 2 root 7 to add 3 root 7, we will be in a position to say that these terms are of the same order, just like we were dealing with this expression here when we are talking of like terms. So we end up adding the coefficients, which is 2 plus 3, so we end up with 5 root 7. So this is how we perform addition when it comes to surds. Likewise, in the second expression, we are having here 3x minus 2x, and since these are like terms, we end up subtracting the coefficients, so we end up having 1x. So in equal measure, when we are considering surds, we've got 3 root 7 to subtract 2 root 7. Since they are of the same order, we are going to subtract the coefficients, so we end up with 1 root 7, which can simply be written as root 7. In the third expression, we are having 2x plus 3y. Now, these terms are unlike, and since they are unlike, there's nothing we are going to do about them, so they remain the way they are. So, in equal measure, let's consider that we are dealing with surds here. So, let x represent root 7 and y represent root 5. So, the moment you have 2 root 7 to add 3 root 5, you'll be in a position to see that these two terms are not of the same order, and so that expression involving surds will remain the way it is. And also in the last expression, you can see that we are to subtract, but these terms are unlike, so there's nothing we are going to do to it. So in equal measure, when we are considering surds, and we've got 3 root 7 to subtract 2 root 5 here, we'll be in a position to say that these two terms involving surds are not of the same order, and therefore the expression will remain the way it is. What about multiplication of surds? Let's look at these two expressions. So considering that we are multiplying these two terms, and we know that these terms are like since they are having their non-x, what do we do here? We multiply the coefficients and we also multiply the unknown separately, and then we combine them by multiplying. So here we have 6 to multiply x squared, which will end up giving us 6x squared here. Now when it comes to surds, it's the same rule that applies, that we multiply the coefficients separately, and then we multiply the surds separately, and then we combine them by multiplying. So here we end up with 6, and then root 7 squared is simply 7 to get our answer here as 42. So here we are dealing with unlike terms. So when you consider multiplication again, we use the same procedure. We multiply the coefficients separately, and then we multiply the unknown separately, and then we combine them by multiplication. So we end up with 6 and then x times y, which is simply xy, to end with 6xy as our solution. So when it comes to surds, it's the same thing that applies. Assuming that x is root 7 and y is root 5, we end up having 2 multiplied by 3, that is the multiplication of the coefficients here, and then the multiplication of surds separately to end up with 6 root 35. And then when it comes to division of surds, rationalization of the denominator will take care of that. Let's consider the following questions. Number 1. Without using a calculator, solve this expression here, leaving your answer in the form a root b plus c, where a, b, and c are integers. 4 marks. To find the solution here, we need to consider the prime factorization of these four surds here. So the first number is the root of 252. So this is the prime factorization of 252, and therefore this surd can be written as root 2 multiplied by root 2 multiplied by root 3, and then multiplied by root 7. So by simplification, you're going to consider the fact that when you multiply root 2 by itself, you end up with 2, and when you multiply root 3 by itself, you end up with 3, and then we multiply this by root 7, whose simplification will end up giving us 6 root 7. The second number is root 72. So the prime factorization of 72, we will end up with the root 2 multiplied by root 2 multiplied by root 2, and then multiplied by root 3, and then root 3 here. So by simplification, we are going to consider the fact that when you multiply root 2 by itself, you end up with 2. And then there will be root 2 here that will remain, and when you multiply root 3 by itself, we end up with root 3. No, we end up with 3. So then we multiply 2 by 3 here to get 6, and then to multiply root 2, so we end up with 6 root 2 as our answer. The third number is root 32. So this is the prime factorization of root 32, so we end up with root 2 multiplied by itself 5 times. So by simplification here, we are going to consider that when you multiply root 2 by itself, we end up with 2, and when you multiply with the root 2 by itself here, we also end up with 2, and then the root 2 at the end will remain. So by simplification, we will end up saying that the answer here is 4 root 2. And then the last number is root 28. So this is the prime factorization of 28, which can be simplified into root 2 multiplied by root 2 and then multiplied by root 7. And so when you multiply root 2 by itself, you end up with 2, and then you multiply by root 7. So our solution here is 2 root 7. So this is how this expression will look like after we've considered the simplification of these surds. So root 52, it will be 6 root 7. So we are going to have here 6 root 7 to add root 72, which we've simplified to 6 root 2, and then we divide by root 32, which we've simplified to 4 root 2, 4 root 2, and then we are going to add root 28, which we've simplified to 2 root 7. So let's now consider the solution so that in the end we leave it in this form. So we are going to consider the solution here by considering the conjugate of the denominator. That means we are rationalizing the denominator, and we said we are going to consider difference of two squares. So for this expression here, its conjugate should be 4 root 2 to subtract 2 root 7. And whatever you multiply on the denominator, you should also multiply on the numerator. So let's consider now the multiplication here. So we've considered the fact that on the denominator side, we are going to have difference of two squares. So the end result, we are assuming that this is like having a plus b to multiply a minus b, where we say that the solution will be a squared minus b squared. So this will serve as my a squared. I'm going to have here 4 root 2 squared to subtract 2 root 7 squared. And then on the numerator side, I need to expand. I'm going to have 6 root 7 to multiply this bracket here, which is 4 root 2 minus 2 root 7, and then plus 6 root 2 to multiply the bracket also, which is 4 root 2 minus 2 root 7. Okay, and then the next step is to open the brackets here, and we said you're going to multiply the whole numbers and then the surds, and then we combine. So this will be 6 times 4, that is 24, and then root 7 times root 2, that is root 14. So we end up having 24 root 14 to subtract the multiplication of this one here, which will be 12 times root 7 squared, which is simply 7. So 12 times 7, that will be equal to 84. And then on this other side, you are going to have 6 times 4, that is 24. And then times root 2 squared, which is 2. So 24 times 2, that will be 48. And then to subtract these numbers, positive times negative is negative. And therefore 6 times 2, that is 12 root 14. So we're going to have here 12 root 14. And then on the denominator side, we can solve this. So this will be 4 squared, that is 16, multiplied by root 2 squared, which is 2. So we end up having 32 as our answer. And then 2 root 7, 2 squared, that is 4, and then root 7 squared is simply 7. So 4 times 7, that is 28. And then the next step we are going to consider here is putting like terms together. We know that when you have 24 root 14 and 12 root 14 here, we can say that they are the same order, and therefore an operation can take place here. So we're going to subtract the coefficients. 24 minus 12, that is simply 12 root 14. And then the whole numbers, you're going to have negative 84 to add 48. So you're going to have here negative 36. And then on the denominator side, you're going to have 32 minus 28, which is simply 4. And then our last step for simplification, since everything is divided by 4 here, we can separate them by considering that this will be 12 root 14 divided by 4 to subtract 36 divided by 4. So we end up having here our answer as we can cancel by 4 1 by 4 3. So we end up having 3 root 14 to subtract 36 divided by 4, which is 9. So this is my final answer, and if you look at it, it is of the form a root b plus c.